All right, welcome everybody to the first of the online lectures. So again, the way the rest of the semester is going to go is you're going to watch these lectures online. They will all be posted all at once. So if you want to binge them, feel free. I probably wouldn't do that, but you can. And then the class time, actual class time, will be still available for you at least on certain days for you to come in and take quizzes, work on projects, ask questions to, I believe, either Dr. Sinclair or Dr. Hassinian will be covering my class. The actual in-person part. So class is basically flipped for the rest of the semester. Watch these videos and then come in again on certain days to take quizzes and work on projects during actual class time. If you don't want to do that, if you don't want to come in and work, I think that's a silly choice, but that's your choice to make. And you won't be counted absent. So that's office hours. I will post in Canvas an announcement of whose office hours you can go to. Again, I'll be splitting those up between other professors in the math department. So you'll have, I will post an announcement there where you can see clearly whose office hours you can go to so that you can go and take quizzes and ask questions and so on and so forth. So that's the plan for the rest of the semester is watch videos outside of class, do work inside of class. Okay, so that's that. Let's talk about, and we're on this topic of elliptic curves, and elliptic curve cryptography is the last topic we're going to cover in this class. So let's get started with it. We're going to talk about elliptic curves today, and then going forward, we'll talk about how we use elliptic curves in cryptography. Okay, so announcements. Everything you need to do, everything is in MyOpenMath. So make sure you're working on everything in MyOpenMath and checking what you've done against the syllabus to see what your grade is going to be. You have full control of your grade. You just need to complete the assessments that are in the syllabus. Let me pull up the syllabus really quick. I'll pause this so that it. So as a reminder, in the syllabus, you can go and find, if you want a B in the class, then you need to meet all the minimum specifications for a C. So you need to complete all of these things, which means you actually need to complete all of these things. And then do the following: complete 80% at 80% or higher, the 13 out of 15 homeworks in MyOpenMath. You need to complete these quizzes and get a B in the cipher breaking project. But again, in the classical ciphers module, you also, for C, need to do these things, and for D, need to do these things. So again, make sure you can check every single box here. In the mathematics of cryptography module, we have these things published for you to be able to work on, and so on and so forth. Okay, so if you've missed 5 classes, and haven't let me know that you were going to miss, and those are unexcused absences, then you cannot get a B. So attendance is also a requirement for this class, and so make sure you check your attendance record, and if it doesn't match up with what you think it should, then I would say that's probably not true, but make sure you check your attendance, and if you have more absences than you think you should, let me know, and we will talk about it. But there you go. You know, whatever grade you want, you know exactly what you need to do to get it. So make sure you've done what you need to do to get the grade that you want. All right, that's enough announcements. Let's get into the topic of elliptic curves. So elliptic curve cryptography was introduced in the 80s, and as we've seen in class, when I look at, when I pull up security certificates, on a lot of different websites, elliptic curve cryptography actually seems to be the most common thing. It's a very commonly used crypto system on a lot of websites today because it has a lot of security with a lot less overhead in terms of needing to generate huge prime numbers. It still uses large prime numbers, we'll see. But you can get the sort of same security from elliptic curve cryptography that you do out of, say, RSA using much shorter keys. So RSA requires keys that have, 600 digits. For instance, elliptic curve cryptography if you look at the keys generated there, are about half the size. So elliptic curve cryptography, again, same security for less overhead, which is really nice. So we're going to talk about elliptic curves soon, but there's a few things that I'm going to assert about elliptic curves that are a little easier to understand for a curve that you're really familiar with, and that's the circle. So let's talk about the unit circle for a second. The unit circle has an equation, x squared plus y squared equals 1. That's one way you can write out the equation of the unit circle. And we say a point on the unit circle is rational if the x and y coordinates are rational numbers. So the points 0, 1, 0, minus 1, 1, 0, and minus 1, 0, those are all rational points on the unit circle because their coordinates are not only rational, they're integers. But are there any others? Are there any others on the unit circle? Let's see. And one reason why this is important, why this matters at all, outside of showing you an example that will kind of help you get used to elliptic curve operations, is the rational points on the unit circle actually lead to Pythagorean triples, numbers that can be the side lengths of a right triangle. So let's give ourselves a drawing here of the unit circle. Perfect. No notes. And I'm going to be using, to answer this question of are there any other rational points on the unit circle, I'm going to be using this point, minus 1, 0, as sort of a base point for us. Okay. And I'm going to pick another point on the unit circle over here that I'm going to call xy. And I'm going to assume that that point has rational coordinates. Okay, so I'm going to, well, let's assume for a second that that point has rational coordinates. So if I assume that, then when I draw this line through those 2 points, the points minus 1, 0 and xy, where x and y are rational numbers, then what has to be true about the slope of that line? The slope, which is y over x minus minus 1, right? Change in y over change in x. The slope here is y over, so y minus 0 technically, over x minus minus 1, which gives me y over x plus 1. The slope of the line through those points, if x and y are rational, has to be a rational number. Okay? That's if I assume x and y are rational. But notice, it's also true that if I don't assume x and y are rational, but I do assume that m, the slope of the line, is rational, then that's also going to force x and y to be rational by the same reasoning. Okay, so this line, if it has a slope that is a rational number, then where it intersects the unit circle is going to have rational coordinates. Okay, so let's use that fact. Let's write down the equation of this line. And let's assume that the slope of this line is rational. Okay, so the equation of this line is y minus 0 equals slope times x minus minus 1, which tells me y equals slope times x plus 1. Right? And I'm going to assume the slope is rational, which will force the point of intersection of this line with this circle to be rational. So assume m equals r over s, where r and s are integers. Okay? All right. So I'm going to write that out. Y equals, well, actually I won't. I'm just going to leave it as m because in a second there's going to be so many r's and s's that I don't want to write that out. All right. So where does this point of intersection happen? That point of intersection, xy, happens where the line intersects the curve x squared plus y squared equals 1, right? So I want to find, that's what WTF stands for. I want to find the point of intersection between the line y equals m times x plus 1 and x squared plus y squared equals 1. In order to do that, that means the x and y values need to be the same thing at the same time. I'm going to plug in the y value here into this circle equation, right? If they have the same y, then I just need to solve for the x's for which that happens. So let's do that. If I plug in that y, I get x squared plus m times x plus 1 squared equals 1. Cool. All right, and so let's write this out. This gives me like x squared plus m squared times x plus 1 squared equals 1, which tells me x squared plus m squared times x squared plus 2x plus 1 equals 1. I'm just expanding that x plus 1. And now let's write this in sort of standard form. I'm going to collect all of my x squareds together. How many x squareds do I have? Well, I have 1 x squared there and m squared x squared. So that gives me 1 plus m squared times x squared plus, how many just x's do I have? Well, I have 2m squared times x. Right, when I distribute that m squared, that's what I'll get. And then my constant term is plus m squared minus 1. That equals 0. Wow. So, what does this tell me? I plugged in my y equals m times x plus 1 into the equation for the circle, and we got this quadratic equation. This is a quadratic equation, and one way to solve this is to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We could do that. However, one thing that we should sort of remember is that the solutions to this quadratic equation are going to be the x values where this line intersects this circle. The one that we're really interested in is this one right here, that x value, right? But we actually already know one of the x values where this line intersects the circle. Can you see what it is? Pause it and take a guess. That's right, it's minus 1. I also know that when x is minus 1, this line intersects a circle. So I know one of the solutions to this quadratic equation. And in fact, you don't even need to guess. Plug in x equals negative 1, and you'll see that x equals negative 1 solves this equation. Okay? So I can use that to my advantage. I know that this has to factor like x plus 1 times something. Well, what's going to be the something that's left? Well, it's going to have a 1 plus m squared times x, right? Because of this 1 plus m squared. And then what else does it need to have? Well, I know that it looks like 1 plus m squared times x plus something, plus blank. So one other thing that we could use is the fact that, where are my? This times this, that'll give me one part of this 2m squared x, but also this times this, when I add that up, I should get 2m squared. So I know that 1 plus m squared, let me call this b for a second, 1 plus m squared times 1 plus b has to equal 2m squared. So then I can solve for b, right? I subtract m squared. That cancels one of those. And then I subtract 1. I get b equals m squared minus 1. Okay. So we have this, and you can go ahead and write this out. C 1 plus m squared plus where am I? Plus m squared minus 1 equals 0. You can FOIL this out, and you'll see that we get the correct thing. I don't even need to actually do that foiling. But there we go. And so I know that x equals -1 solves this. Cool, easy. And I also, again, notice I used the fact that this coefficient here told me what this other solution kind of needs to be, right? That's going to come into play later when we're looking at elliptic curves. Okay. All right, but let's solve this. X equals -1 is a boring solution. I don't care about it. The other solution that I get from this is by setting this equal to 0. Okay. So when I set that equal to 0, I get 1 plus m squared times x plus m squared minus 1 equals 0. So that tells me x equals 1 minus m squared over 1 plus m squared. And now if m equals r over s, then this tells me that x equals 1 minus r squared over s squared over 1 plus r squared over s squared. Multiply top and bottom by s squared, and I get s squared minus r squared over s squared plus r squared. So I know the x coordinate of this point on the unit circle, and I can plug that back in for y up here. Y equals m times x plus 1 up here. To figure out what the y coordinate is, I get y equals r over s times x plus 1. So that's like s squared minus r squared over s squared plus r squared. Plus 1, well, 1 is s squared plus r squared over s squared plus r squared. So it gives me r over s times, when I add these two things up, I get what? 2s squared over s squared plus r squared. And bingo, bango, I get 2sr over s squared plus r squared. Okay, so I have my x and y coordinates, and they are, if s and r are integers, then this is a rational number. So let's go to Desmos really quick and make sure that this works. X squared plus y squared equals 1. There's my circle, my unit circle. Here are, so I'm going to call s some integer. We'll start with 1. S is going to be from, I don't know, 1 to 1,000 with a step size of 1. So S is always an integer in Desmos. And same thing with R. We'll say R is 2. Desmos likes to plot circles there, so I'm going to hide that. 1 less than R less than 1,000, for instance, step size of 1. And let's make sure that these points are actually on the unit circle. So we've got S squared minus R squared over S squared plus r squared, and 2sr over s squared plus r squared. There we go. So that point clearly lies on the unit circle, and as I drag s around, maybe I went a little too big. Let's go s between 0 and 100 so that as I drag s around, we see that it stays on the unit circle. Okay. And because s and r are integers, then these coordinates, s squared minus r squared over s squared plus r squared, are rational numbers. 2sr over s squared plus r squared gives me 12 over 13. 5 over 13 lies on the unit circle. 8 over 17, 15 over 17 lies on the unit circle. There we go. We get a bunch of different rational coordinates on the unit circle, which is very, very cool, I think. And so one other thing that this tells us is that because these coordinates squared, when you add them up, equals 1, if you multiply both sides by s squared plus r squared, you get Pythagorean triples. So notice 168 squared plus 425 squared equals 457 squared. Wow. So I know that there's a right triangle that has a side lengths of 168 and 425 and a hypotenuse of 457. That's pretty cool. And I can get another right triangle. Let's do a positive one. So, 141 squared plus 1,100 squared. Does that equal 1,109 squared? Why, yes, it does. I'm checking, but I really don't even have to because I know that's going to be the case. Okay, so this is how we find rational points on the unit circle. And the main thing that I want you to take away from this was this argument right here. We plugged into an equation to find an intersection of a line and a curve. And then at this point, we said, well, hold on, we know one of the solutions already. So let me use that to my advantage to sort of factor this into this times something. And then once we know that something, we can figure out very easily what the other factor is. Okay, that's the key thing I want you to take away here is we got here by knowing a solution already. All right, so you might say this is weird and doesn't seem useful. It is useful, and but the main takeaway was a certain technique. Okay, so now let's talk about elliptic curves. An elliptic curve is an equation of this form. Y squared equals x cubed plus ax plus b, where 4a cubed plus 27b squared is not equal to 0. So let's look at some examples. We're just going to go to Desmos, instead of rigorously writing this out. So a circle is not an elliptic curve, right? You could rearrange it to be like y squared equals 1 minus x squared, but that's not the form that we want. Okay, so I'm going to look at y squared equals x cubed plus ax plus b. I'm going to add those sliders. So as I move these sliders around, we get different elliptic curves. The two main shapes of an elliptic curve are things like this, sort of one connected piece, and this sort of kind of egg shape and then a hyperbolic looking piece. Okay, these are the two main shapes that we get. Now you might notice that there's one shape I'm kind of leaving out, and that's the shape that we get when these two pieces kind of collide with each other. And that's going to happen exactly when this 4a cubed plus 27b squared is equal to 0. Okay, and so we can see that by if I set 4a cubed equal to negative 27b squared, then what would I get? I would get a cubed equals minus 27 times b squared over 4, and then take all of that to the 1/3. Okay, so now it's a guarantee that 4a cubed plus 27b squared is equal to 0. Desmos is a little stupid, and so there's round off error going on here. But notice the shape of this curve. No matter what I do, the shape of this curve for b greater than 0. If b is less than 0, then we get some weirdness. But no matter how I increase b, I'm always getting this weird self-intersection right here. Okay, and that's what we want to avoid. That's what saying this thing right here, 4a cubed plus 27b squared is not equal to 0. That prevents this self-intersection that we're going to not want. We do not want that self-intersection right there. Okay, but every other a and b is permissible. And most of the time, it's actually pretty rare that if you just pick a elliptic curve at random, that you'll get 4a cubed plus 27b squared is equal to 0. Okay, so it's actually pretty uncommon for that to happen. And you can see that it only happens in some pretty weird cases. So these are the two main types of elliptic curves. This sort of two piece, and then this sort of one piece elliptic curve. Okay. The name elliptic curve does not come from ellipses, clearly. We're not getting ellipses out of this. Even this thing isn't an ellipse. It's some sort of lopsided ellipse if you want. But the main place that these come up is cryptography, clearly, but also like how they were discovered was through in calculus when you're trying to find arc length. The formulas that you get from those complicated integrals lead to things that look like this. So that's where the name elliptic curve comes from, is in trying to find the arc length of an ellipse, you get these sort of elliptic curves out of the integral that are very difficult to evaluate, and in fact, impossible to evaluate in some cases. Wow. Very cool. All right. So let's talk about how we add points on an elliptic curve. Okay, so it turns out the points on an elliptic curve form a group, just like the points in Z mod 101 under addition, right? So we're going to decide how should we add 2 points together on an elliptic curve to make sense of the operation of addition. And sadly, it is not just add the coordinates together. Okay, so let me draw an elliptic curve here. Maybe it looks something like this. And then it does something like, let me just copy one that's over here. Maybe it does something like this. Okay, so here's an example of an elliptic curve. Okay, to add points on an elliptic curve, let me say I have this point P, which has coordinates x1, y1, and this point Q, which has coordinates x2, y2, and I want to add those points together to get a third point on the elliptic curve. If you just add x1 and y1 and y1 and y2 and get those coordinates, that's almost certainly not going to be on the curve. Okay, so the way we add points, quote unquote, is by connecting these 2 points, P and Q, and finding the point of intersection between P and Q. This point right here. Now that point is not P plus Q. We're about to do one more weird thing. We're going to call this PQ. Let's call this R tilde, which we'll say has the coordinates x3, y3, and we'll figure out what those coordinates are in a second. But once you have R tilde, then the last thing you do to add 2 points on an elliptic curve is you take that point R and you reflect it about the x-axis. Okay, so you take the y coordinate and you flip it. You make it negative. So this is the point R equals P plus Q, which has the coordinates x3 comma minus y3. Okay, so we take the original point of intersection and we flip it about the y-axis. Now, let's see if I have the elliptic curve. This is the elliptic curve y squared equals x cubed plus ax plus b. And I have these 2 points that are on the elliptic curve. Let's see if we can figure out x3 and y3 from those 2 points. Okay, so I know x1 and y1 satisfy, if p is on the elliptic curve, x1 and y1 satisfy y1 squared equals x1 cubed plus ax1 plus b. Same thing with y2 and x2 and y2. I know y2 squared equals x2 cubed plus ax2 plus b. Okay, now the slope between these 2 points is just m equals y2 minus y1 over x2 minus x1, right? Change in y over change in x. That's a 2. Okay, and so the equation of the line through those 2 points, there's a couple of different ways that you can write it, but the equation of that line is y minus, I'm just going to base things around p arbitrarily, y minus y1 equals m times x minus x1. Or in other words, y equals y1 plus m x minus x1. All right. So what we want to do, we know these 2 points lie on the elliptic curve. We want to figure out where else does this line intersect the elliptic curve. It's always guaranteed with the choice of 4a squared, 4a cubed plus 27b squared not equals 0. You're always guaranteed that you're going to have a third point of intersection. Okay, so let's find that third point of intersection by plugging this equation of our line into the equation of the elliptic curve. Okay, so I'm going to plug that into the equation y squared equals x cubed plus ax plus b. We want to find the point of intersection of these two curves. Okay. All right. So we're going to do what we did last time. Plug in y into the elliptic curve. Okay. Let me add a blank page here. When I do that, I get y1 plus m times x minus x1 squared equals x cubed plus ax plus b. Okay, and we want to solve this this equation here for x now. The only unknown, a and b, x1, y1, m, all those things are known. Okay, so to do this, let's expand the square on the left. It gives me y1 squared plus m squared times x minus x1 squared equals x cubed plus ax plus b. Now I'm going to move everything over to the right. I'm going to swap sides, but I'm going to move everything over to one side. And when I do that, I get x cubed minus m squared times x minus x1 squared. Then the linear term is plus ax plus b minus y1 squared. All right. And then I'll expand that square there, and I get, and by the way, this is equal to 0. I'll expand that square there. I get x cubed minus m squared times x squared minus 2x1x plus x1 squared plus ax plus b minus y1 squared equals 0. And now writing this in standard form, let's look at this. We've got x cubed plus, what do I have attached to x squared? Well, minus m squared times x squared, right? That's the only thing that has an x squared. Then what's the x to the first term look like? Well, I'm going to have right here minus m squared times minus 2x1. That gives me plus 2mx1. And then plus a from that guy. Plus a. That's the only stuff attached to an x to the first. And then finally, we've got plus our constant stuff. So b minus y squared, y1 squared. Plus, where am I? B minus y1 squared, and then minus m squared x1 squared. All right. At this point, you might say, this is very gross. But something to remember is think about what we did with the circle. Do you know, I want to solve this equation. I can solve it if I can factor the left-hand side completely. And you might say, no way I can factor that thing. But remember, we already know 2 x's that satisfy this, right? Because x1 and x2 were x coordinates for points that live on the ellipse. I know that x1 and x2 automatically solve this equation. Okay, so if I want to factor this, I know that this is going to look like x minus x1, x minus x2 times x minus something. Okay, equals 0. And we want to find x3. So I'm just going to call it x3. Okay? This is the thing that we actually want to find. These two things we know. All right? So now let's expand that thing on the left. And really, I don't even need to expand it fully because I know the x squared term up here. Okay, so let's just ask ourselves what's going to be attached to the x squared term when I expand this stuff? Well, how could I get an x squared out of this? I could do this x times this minus x cubed, right? So the x squared, so x cubed is just going to be x cubed, plus the x squared thing is going to have minus x cubed attached to it, or sorry, minus x3 attached to it. How else could I get an x squared? Well, this x times this minus x2, so that's going to give me a minus x2. How else could I get x squared? Well, this x times this constant x1, minus x1. So that gives me minus x1 there. Okay. And then honestly, I don't care about the rest of it. I do not care about the other parts because this gives me enough to solve for x3, right? Because again, we know m. Oh, give me the laser pointer, please. We know m, and we know x1 and x2. So this lets us solve for x3. How? Well, match up the x squared terms. We get minus m squared equals minus x3 minus x2 minus x1. Cancel out all of your negatives. Cancel. And we get m squared, which again we know, equals x3 plus x2 plus x1. And so this tells me the x coordinate. x3 is m squared minus x2 minus x1. That's the x coordinate of the third point that lives on the elliptic curve. And once you know that, then you can find y3 by plugging that in up here. Okay, so I can get y3 by saying y3 equals y1 plus m times x3, which we know now, minus x1. Okay. And then finally, to get your p plus q, you take x3 comma minus y3. Okay. So this is how we add points on an elliptic curve. And you can maybe see, because this is so hard to do, why elliptic curve cryptography is considered so secure. Okay, so p plus q is x3 minus x3 comma minus y3, where x3 equals m squared minus x2 minus x1. P, by the way, is the point x1, y1. Q is the point x2, y2. So x3 is m squared minus x2 minus x1. M is y2 minus y1 over x2 minus x1. And y3 is y1 plus m times x3 minus x1. Gross, but it works. Okay. All right. So that's how you add two different points on the elliptic curve, on an elliptic curve. So let's do this. We're gonna let Desmos do this. Before we talk about taking a multiple of an individual point, let's add 2 points on an elliptic curve here. So let's let Desmos do this. Again, we just need to calculate now. X3 is m squared minus x2 minus x1. We'll call this x1, y1, and this x2, y2. M is y2 minus y1 over x2 minus x1, and y3 is y1 plus m times x3 minus x1. Okay, so let's go plug these things into Desmos. Okay, first, I'm looking at the elliptic curve x cubed plus 1x plus 1. So here's the elliptic curve we're looking at. Notice 4a cubed plus 27b squared is not 0, so it's a genuine elliptic curve. We're looking at the points 0, 1 that are on this curve, and 1/4, comma, -9/8, which is also on this curve. Okay. So we need m is y2 -9/8, -9/8, minus y1, so -1, over x2, which is 1/4, minus x1, which is 0. So there's our slope between those 2 points. And now I can calculate x3 is m squared minus x2, which is 1/4, minus 0. So there's x3 is 72. And y3 is y1, which is 1 plus m times x3 minus x1. Which gives me, why aren't you spitting that out, Desmos? Oh, because I don't have a y1, sorry. Minus x1, which is 0. -611. So finally, to get the point P plus Q, we take the x3 coordinate, 72, and negate the y3 coordinate, 611. Let's zoom out and see if that's on this elliptic curve. So I want to go from, let's go from -1 to, we need to go to 72, so let's go to 80. And y-axis, let's go from -1,000 to 1,000. Okay. And we can see that that point does indeed lie on this elliptic curve. Bananas. Also, you might be, I am genuinely surprised that this point has such nice coordinates, right? The Q here, 1/4, comma, -9/8 is gross. Okay. But let's look at the line that goes through the original 2 points. That would be the line y equals 1 plus m, which we've already calculated, times x. Okay, so there's that line, and if you want to find the point of intersection, you get it right there at 72, -611, which we already knew, right? We already knew that point of intersection. And then finally, again, the really weird thing about adding points on elliptic curves is you flip it. There's a special reason why we do that, but you flip it across the x-axis to get that final point for adding 2 points on an elliptic curve. Okay, so that's how we add 2 different points on an elliptic curve. You can memorize these formulas if you want. I will give them to you if you're working on a project. You can look back at your notes if this comes up on a quiz. There's no elliptic curves quiz, by the way. But if you're working on an elliptic curves project or something, look back at the notes, look at these formulas. But you know, P plus Q is x3, comma, minus y3. Okay, so when we did this, we got our slope was -8.5, I think, if I remember right. -8.5. Then x3 was 72, and y3 was -611. So that gave us 72, comma, 611. It's weird, I know, but that is, it's a guarantee that when you define addition of points on a curve, on an elliptic curve in this way, the set of points on the curve under this operation of addition forms a group. Okay. Now, the only weirdness comes into play if, like, what if I want to do P plus P? What if in this last example, I wanted to do, switch to Desmos. What if in this last example, I wanted to add p to itself, the point 0, 1, to itself, 0, 1? Well, in order to do that, technically you need calculus to find the equation of the tangent line to the curve at the point P. Okay, so the tangent line is the line that is tangent to the curve. So let me draw now some other elliptic curve. So if I want to add the point P to itself, so this is the point P, which we'll call x1, y1, then I still just need the slope of the tangent line, or the slope of a line. The tangent line is the line that just touches the curve at the point you're interested in. So, but the idea is still find that slope of that line, and then find the point of intersection, and then flip that point of intersection. So we'll call this point, just to be consistent. So this is the point 2P, which has coordinates. Or sorry, that's not the point 2P. Sorry, we're going to call this r tilde for a second, which has coordinates x3, y3. And then I'll flip that about the x-axis again. This point down here is the point 2P, which has coordinates x3 comma minus y3. Okay, so the only thing we need to do that's more than, or I guess different than what we did before, is we need the slope of this tangent line. Okay, now for the equation y squared equals x cubed plus ax plus b, from calculus, you can use implicit differentiation. If you haven't had calculus, then ignore what I'm saying until I tell you what the slope of the tangent line is. Okay, but from calculus, you can use implicit differentiation to say that this is 2y, y prime, where y prime is that slope of the tangent line that we care about, equals 3x squared plus a. So that y prime is 3x squared plus a over 2y. This is the slope that we're going to use. And in particular, the slope of the tangent line, m, is 3x1 squared plus a. That a is coming from the elliptic curve, divided by 2y1. Okay. So now I know the equation of this line is y equals y1 plus m times x minus x1, where m is this 3x1 squared plus a over 2y1. Okay. And so I'm going to plug this into the equation of the ellipse again. Okay, so let me add one page. So the equation of the ellipse is y squared equals x cubed plus ax plus b. The equation of the tangent line is y equals y1 plus m x minus x1. Again, so plug that into the equation of the elliptic curve, and honestly, at this point, we actually don't need to go through all the work. The equation is going to come out exactly the same for what x3 and y3 are. x3 is going to be the slope of the tangent line minus, so we had an x2 minus x1, but we're just going to treat x2 and x1 as the same thing. So this is going to be minus 2x1. Okay. And then y3 is going to be y1 plus m times x 3 minus x1, just like before. Okay. So shortcut the work. Shortcut by plugging into what we already have. Okay. And again, m, the really truly weird thing is that m is 3 x1 squared plus a over to y1. Okay. And then 2p is given by x3 comma minus y3. Okay, so we can do all of that to figure that out. So let's actually look at one more example of finding on an elliptic curve the multiple of a point P. Okay, so on the elliptic curve, y squared equals x cubed plus 1. Find 2p if p is the point 2, 3. So the things I need, again, x3 is m squared minus 2x1 for adding a point to itself. M is 3x1 squared plus a over 2y1. That's something that you're just going to have to memorize or keep going back to the notes to look up. And then y3 is given by y1 plus m times x3 minus x1. So let's calculate these things in Desmos. Let me do a new Desmos page. So y squared plus equals x cubed plus 1. So there we have that. That point, the point 2, 3 should lie on this elliptic curve. There we go. And we want to find that point added to itself. Okay, so I compute m equals 3 times x1, which is 2, so 2 squared, plus a is 0 here, right? If I do plus ax plus b, then a, in order to get a x cubed just plus 1, we have to have a is 0. Okay, and then over 2 times y1 is 3. So our slope is 2 there, and we can verify that by saying, well, y equals y1, which is 3 plus m times x minus x1, which is 2. There's our tangent line right there, and you can actually see where that intersects the curve. So we should get that this the 2p is going to be 0, 1. Let's verify that. So x3 equals m squared minus 2 times x1. Well, x1, sorry, is 2. There we go, 0. So x3 is 0. y3 equals y1, which is 3, plus m times, where are we? x3 minus x1 is 2. So we get 0, negative 1. That verifies that point of intersection there. And then finally, I flip the y coordinate to get 2p, which is x3 comma minus y3. There is 2 times p. Okay, that's how we calculate that. Again, use Desmos. Use Desmos a lot. So there are some formulas that you kind of have to memorize here to really get into how do I add 2 points on the elliptic curve. But once you've done this, you can verify. It's tedious, so I'm not going to verify it. Trust me, that this forms a group under addition, plus with one little extra thing that I haven't mentioned that I'll mention in the next video. But this is how we add 2 points on an elliptic curve. Okay, so practice is my suggestion. Practice, practice, practice. The homework will have a lot of these problems on it that you can practice, practice, practice. Okay, it's a very very formulaic, but some of the formulas are hard to remember, I acknowledge. So that's it for the beginnings of elliptic curves. Again, practice, 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 and you'll be able to add points together on elliptic curves in no time. Next time, we'll talk about one extra thing we need to add to this idea to turn this into an actual group under addition, the points on an elliptic curve under addition. And then we'll talk about, how is this used in cryptography by introducing prime numbers and elliptic curves with only coordinates mod p. Okay. So that's that. Thank you all. If you have any questions, feel free to email me or go to Dr. Hassinian's office hours, which I will post on Canvas or it should be posted on Canvas by the time you're watching this video. Okay. Thank you all. Have a great day, and make sure you check out the next video when you're ready. See you when I see you.